Building structures to reach space surely predates the modern concept of rockets, probably going back at least to the Tower of Babel. There are a lot of good reasons why humanity should explore this more, and there are also a lot of good practical reasons why we haven't done so yet. One of the most popular concepts is the space elevator. The great difficulty with space elevators is the vast distance involved. To reach geostationary orbit, a structure some 35,000 kilometers tall is required, terminating in the middle of the radiation-dense Van Allen belt. For a compressive design, the weight would far exceed the material strength of any known materials. However, by extending the structure beyond geosynchronous orbit, nearly a third of the way to the Moon, and using a counterweight, the centrifugal force caused by the Earth's rotation would create a tensile structure, which could theoretically be built using a carbon nanotube cable. Carbon nanotubes, however, are a newly discovered material, and realistically speaking, we are a long ways from having the manufacturing capability to produce 100,000 kilometers of carbon nanotube cable. We are even further from having practical engineering experience with making even simple structures with carbon nanotubes. The whole space elevator concept, unfortunately, hinges upon this novel material. There are fortunately other alternatives. The buoyant inflatable space shaft approach is one. However, since buoyancy requires atmosphere, this concept is limited at best to low Earth orbit, and by itself does not immediately present a solution to achieving orbital velocity for launched vehicles, without resorting back to rocketry. It does at least perhaps obviate the need for multiple rocket stages, however. An orbital ring is a space launch concept that consists of a ring in low Earth orbit just above the Earth's atmosphere, attached to the Earth's surface by downstations which provide access to the ring. This centrifugal structure works by propelling ferromagnetic projectiles through the circumnavigating tube at superorbital speeds. The centrifugal force is designed to balance the gravitational pull on the entire structure such that the downstation tethers are neither in compression nor in tension. Thus, unlike the traditional space elevator concept, this launch structure does not require development of exceptional materials. Furthermore, situated in LEO requires a tubular structure only 21,000 kilometers long, plus about 120 kilometers of structure for each of the 7 downstations. These would tentatively be located in Kenya, Gabon, Brazil, Ecuador, Jarvis Island, New Guinea, and Indonesia. The equal axis around the equator makes this perhaps the most viable space project geopolitically speaking, particularly since it provides both a platform and a conduit for space solar power, enabling Buckminster Fuller's vision of connecting a worldwide electrical grid. The acceleration of the active projectiles is powered by a small fraction of the space solar power collection. Higher orbital and interplanetary escape velocities from this platform can be achieved by rail launch, with acceleration at comfortable human levels made possible by the vacuum environment and long potential rail distances. An orbital ring system is also expandable into tiers. For instance, a secondary ring could be built to assist in interplanetary launches, possibly resembling Jim Klein's elliptical space escalator concept. Or a secondary circular ring could be situated in between the inner and outer Van Allen belts. A ring at this elevation would eliminate the need for satellites almost entirely. While not quite as efficient, there is absolutely no reason that orbital rings cannot be built at higher latitudes to serve those populations. The possibilities are endless. One thing that is certain is that an efficient means to escape Earth's gravity well is an absolute requirement if life is to expand throughout the galaxy and beyond.